Hi, this video is about both pre-flight fuel planning and fuel management and decision-making during flight. I'll break it down into three aspects. Calibration, meaning knowing the capacity and consumption of the aircraft you're going to fly. Flight planning, meaning specific planning for a specific flight or journey. And in-flight planning and management, which means monitoring, managing, and reacting to the fuel situation as the flight unfolds. So, starting with calibration, the first question is how we know what is the usable fuel capacity of the aircraft. That might seem obvious. Look at the AFM or POH and it will tell you. But tanks get dented, bladders get kinks, there could be sludge or debris inside. It's likely that no one has checked the actual capacity for many years, and it's unlikely to be more than advertised, more likely to be less. You can defuel and refuel. This is not as difficult as it sounds. You can get a siphon and containers suitable for fuel from eBay, but be very careful as it's a hazardous procedure. If you don't know what you're doing, get trained. When you've got out all you can, in an avgas engine, run the engine till it stops, as that's the only way of knowing what's usable. If you have an aircraft with multiple tanks per wing, you can run tanks dry over a couple of flights and then refuel, taking careful note of what goes into that tank. Thus, if your fuel system permits, you would run the outers dry on one flight, refuel them, then run the inners dry on the next. If you have one tank per wing, this is a slightly trickier thing to do, as you'll then be landing with a fuel imbalance. If you are going to defuel and refuel, take photos of the fuel gauges at a minimum, empty, quarter, half, three-quarters, and full tanks. It's a good idea to mark the result, as it will almost certainly be different to the markings on the instrument. You might also consider calibrating a dipstick. Obviously, if you rent the aircraft, you're unlikely to be able to do this in advance, and then the AFM is the only way. The next thing you need to know is the actual consumption you're likely to encounter. Without instrumentation, this is difficult to tie down. Even though the AFM gives book figures for different altitudes and power settings, a fractional difference in mixture or even atmospheric pressure can make a substantial difference. And as aircraft and their engine age, they will diverge from book figures. Also, the adjustment of carburetors, injectors, and controllers is unlikely to be as it left the factory. The best way is by experience of the particular aircraft. Once you've flown it under a variety of regimes over a number of hours and have carefully noted the refueling figures compared to expected, you'll have a pretty good idea. But if you rent or if you fly intermittently, that's a problem. And also remember that your own aircraft will change over time, so figures you calculated a few years ago may no longer be true. Equally, if the aircraft has had maintenance work on the engine, it can come out differently to how it went in. The best thing is to have a working, accurate totalizer. These not only tell you your consumption, but also plug into your navigator to give you predicted fuel at destination. More of that later, but for the moment it's important to ensure that the totalizer is calibrated. This entails adjusting the K factor in software. The manual will take you through this. I've owned a number of aircraft with JPI totalizers, and I've managed to get them accurate to within 1%, so I know my fuel flow precisely. People often say not to trust the fuel gauges in light aircraft, and I must say I tend to agree. But they do provide a gross approximation and can be crudely adjusted, so that's worth doing. If nothing else, they provide a visual warning that you should be giving fuel a thought. I recently collected a light aircraft I hadn't flown before, having calculated the fuel from the POH, and was surprised by how fast the gauges move. So I landed and discovered that it was using about 30% more than I was expecting. So don't completely dismiss the gauges as junk. Finally, it's worth understanding the benefits and pitfalls of lean of peak operation. I'll discuss it in a moment, but it's not something I can deal with in detail here. The course notes from a weekend-long seminar PPLIR Europe organized a few years ago are hundreds of pages long. It's a big subject. Maybe I'll make a video about that alone one day. But it can reduce fuel consumption quite markedly, maybe a 20% reduction for a 5% loss of speed. It's what enabled Lockheed Constellations to cross the Atlantic and strategic bombers to reach their targets. It's only suitable for injected engines, and it's at its best on turbocharged aircraft, but it's worth investigating for your operation. So, enough about general planning. Let's move on to planning a particular flight or series of flights I say series of flights because it's becoming increasingly difficult to ensure that avgas is available at all destinations, and prices between them can vary so much. Islay in Scotland costs 6 times as much as Jersey and the Channel Islands, so your fuel planning task may well cover multiple flights. Although I'm not entirely convinced by them, let's start with the rules. We're in a changeover period at the moment in that EASA have recently changed its rules for non-commercial operations, and the UK is slowly thinking about following suit. FAA rules are different again. As many of our members fly between EASA states and the UK, often flying FAA aircraft and licenses, this raises the interesting question of how the rules apply to airspace, license and registration, and how they apply to a flight which crosses the boundary. I can only suggest that you follow the most restrictive of the three so that the matter cannot be raised by the authorities or insurance companies. So let's start with EASA rules as they are and are likely to remain. It's your responsibility to ensure that you have enough fuel, taking into account the met conditions, anything which affects the performance of the aircraft, any delays that are expected in flight, and any contingencies that may reasonably be expected to affect the flight. The main thing about the new rules is that the pilot in command must plan an amount of fuel to be protected as a final reserve to ensure a safe landing, taking into account the outcome of an emergency landing and its likelihood. In other words, you must be more careful about flying at night in strong winds over oceans than flying by day in benign conditions over farmland. That's your judgment call. The pilot in command must have enough fuel to fly to destination, then to the alternate, and land with final reserve intact. If no alternate is required, you only need enough to land at your destination with final reserve. But, to be honest, that strikes me as more than a little silly thing to do. But the bottom line is that you must take responsibility for landing with final reserve fuel. If you're in a position where any delays, holding, or leg extensions may result in landing with less than final reserve fuel, you must declare minimum fuel. If it looks like you're going to land with less than final reserve, you must declare Mayday, Mayday, Mayday fuel. So the EASA requirement is for trip fuel plus contingency plus alternate fuel, if an alternate is required, plus final reserve fuel, FRF. The pilot can decide what the FRF is, but the AMC recommends for IFR 45 minutes at holding speed at 1500 feet, for VFR 30 minutes at holding speed at 1500 feet. It won't affect those watching this video, but for completeness, if you're on a local flight within sight of the aerodrome, the recommendation is 10 minutes at max continuous power. In summary, the FRF is at your discretion, but must then be protected as a reserve, not used in flight. Your in-flight planning and decision-making must enable you land somewhere with FRF. If you cannot, you must call Mayday fuel. Minimum fuel means that if there's any further delay, I will declare Mayday fuel. The situation in the UK is in flux. The UK still uses the old EASA rules, but is considering changing them to be closer to the new rules I just explained. But I better explain the current situation so you know what the rules are for the time being. In reality, they're not very different. For VFR, remaining in sight of the landing airfield, you must carry 10 minutes spare fuel. If flying en route by day, you need an extra 30 minutes, and by night an extra 45 minutes. For IFR, if no destination alternate is required, you need an extra 45 minutes at normal cruising altitude, and if a destination alternate is required, enough to fly the planned route, then to an alternate aerodrome, and then enough to fly for 45 minutes at normal cruising altitude. But in either case, you must also allow for contingency, taking into consideration forecast meteorological conditions, anticipated ATC routings and delays, failures, including loss of pressurization, engine failure while en route, and anything else that might cause delay or increase consumption. Inaccurate leaning and extended use of carb heat, alternate air, and cowl flaps all cost fuel efficiency. One thing that MEP pilots sometimes forget is that cabin heaters burn fuel, eating into their contingency. The rules also allow for in-flight replanning, whereby unused contingency fuel can be repurposed as en route fuel. This allows for the en route alternate, whereby you plan for somewhere short of your destination, but if you haven't used your contingency as you approach the alternate, you can continue to destination. This is particularly useful if you expect substantial shortcuts. I'll talk more about that in the next section about replanning in flight. These rules are not so different from the EASA rules, but EASA now offers more flexibility while placing more responsibility on the pilot. Under EASA, landing with too little fuel becomes what we in the legal business call a strict liability offence. Either you have enough fuel or you don't, but it's your responsibility to ensure that you have. But having gone through the rules, do we think they're pitched at the best level of conservatism? They assume landing with final reserve fuel after holding and diversion. Are we comfortable with taking things so close to the wire? I assure you that I personally am not. I get very uncomfortable if I have less than 90 minutes of fuel. I recently was kept low in a turboprop, resulting in more fuel burn than I planned, and was considering landing at a closed airfield, even though flying to destination actually had me landing with more than FRF. We surround ourselves with redundancy and fail-safe, but fuel exhaustion has no backup. On the other hand, they expect us to plan for extended IFR routes that we're most unlikely to fly. Are we comfortable with that? Are we going to plan to break our journey because the Eurocontrol routing is 30 or 40% greater than Great Circle, something that ATC will never allow to happen? Here are some real-life routings which are patently ridiculous, but for which we are expected to carry enough fuel. So, on the one hand, I'm saying that the rules are too liberal, on the other hand, that they're too conservative. That's because no one size fits all. There are so many different considerations, most importantly, the availability of suitable diversions. Crossing sea and remote terrain, and at night when many airfields are closed, is very different from flying over Europe by day. In formal planning, this is the concept of en route diversions, but informally, you can just increase your risk tolerance because you know you'll be flying near to many suitable refueling stops. Avgas availability is also becoming an issue, and there are some areas where it's increasingly difficult to find. Norway and Greece spring to mind, but it's becoming a problem in many places in Europe. That means that it's not enough just to run low on fuel and then start looking. You should have suitable tech stops in mind, having checked Avgas availability in advance. Remember that the AIP is not enough. You must check NOTAMs as well, and even be sure that you have the means to pay. There are some places where only carnet is acceptable. Customs and immigration will also be a consideration if you've crossed the Schengen border. Together with the vagaries of ATC routing, probably the biggest unknown in fuel usage is wind. Generally, aircraft are more fuel efficient at higher altitudes, but equally, wind increases with altitude. And while that's good with a tailwind, remember that headwinds are more common than tailwinds. 55% of all wind directions slow you down and only 45% help you. If you don't believe me, dig up your old whiz wheel and play. So it's one thing to know what your ground speed and efficiency are, both of which your navigator will tell you if you have a fuel totalizer, but how do you know whether you are best to climb or descend? You can use the forecast, of course, but my experience is that they're not as reliable as in-flight information. The air data computer, if you have one, will give you an accurate reading for your current altitude, but you have to change altitude to discover how it changes. Probably the best sources for up-to-date wind forecasts in flight are Goltzer and Connext, with Goltzer having every advantage of capital and running costs and ease of installation. From the data, you can calculate your prospective ground speed and efficiency at any altitude. Your efficiency will vary with power regime. Generally speaking, lower power settings will give you greater range even in the face of headwinds. I've spent happy hours deriving theoretical efficiency and range tables for my aircraft at different altitudes in different wind conditions. And even against a 40-knot headwind, range is greater at 55% than at 65 or 75%. However, in my aircraft, 55% is lean of peak and the others are rich of peak, so your results may vary. It's not difficult to derive these figures from the POH. It's such an obvious calculation, I'm surprised that most POHs don't include it. So, we've talked about planning in general and planning for a particular flight. Let's end by talking about fuel management once we're airborne. How do we know how much fuel we've used and how much we have left? If we have a calibrated totalizer, there's no issue, provided you remember always to register fueling accurately. But that is no mean feat on many of them, as they have the worst human interfaces known to man, enough to get the average saint curse in the heavens. But if you don't have a totalizer, you need to do calculations, which will invariably be less accurate and perforce conservative. The most basic estimation is to know how much the aircraft uses per hour, And some schools and clubs tell you to work on X litres per hour and leave it at that. But that leaves so many questions unanswered. Generally, the schools will assume that you will not be leaning, but even rich of peak leaning can easily reduce consumption by 30% or more. But it also doesn't take into account taxiing, takeoff, and climb. The school's estimate will presumably cover anything up to circuit, maximizing consumption. How can an hour at cruising altitude come close to an hour in the circuit? So, if you're going en route, I would forget about the simple fuel per hour calculation and dig into the POH, which should give you fuel figures for climbing to altitude and for fuel flow in different power configurations. But those figures will assume perfect leaning, a new engine, and a clean airframe, which, unless you're very wealthy, you're unlikely to get. You also need to recalculate for every change of altitude or power. Most of the flight planning apps offer fuel plans, and this can make the process easier, but remember that it's garbage in, garbage out. So make sure that the figures are correct for your planned altitude, rates of climb and descent, and so on. You can use the gauges, of course, with all their shortcomings, as I said before, but if you've had the opportunity to calibrate them, they do give a reasonable idea. Whichever of the four methods you use, totalizer, hourly fixed rate, POH or gauges, the secret is always to check carefully what you put in compared to what you expected. You can then refine your calculations in the light of experience. Let's talk a bit more about leaning. Again, there are a number of techniques depending on the equipment you carry. Don't take any notice of the old wives' tale about not leaning below, for example, 3,000 feet. That is for absolute beginners based on a fear that their engines will stop and they won't have the gumption to push the control back in to restart it. You should lean in the cruise in any aircraft, with a mixture control, at any altitude. If there's no EGT gauge, there's little you can do other than the classic pull back the mixture until the engine runs rough, then push it in a little. This is easiest to do if you have a vernier mixture control, as you can get used to how many turns you need to make. On my little darling Rally, it is so rough and ready that the engine suddenly stops and you just have to push it in a bit to restart it. Every aircraft's different. What you're actually doing using this technique is finding peak EGT on the first cylinder to go lean of peak, then bringing it back rich of peak. If you have just one EGT per engine, you can be a little more sophisticated, but remember that all the cylinders will be different and you're only looking at one of them. But you can lean until you see the temperature reach its peak, then enrichen it until it's 75 degrees Fahrenheit, cooler than peak. On most EGT gauges, there's a cursor. If you normally fly at the same power setting at the same altitude, you can just set the cursor to 75 degrees Fahrenheit rich of peak, and then on future flights, just put the EGT on the cursor. Do be careful if other people fly the same aircraft, as they may move the cursor to match a different power regime or altitude. If you have an engine monitor with EGTs for each cylinder, it becomes much easier to lean precisely and to fly lean of peak, which consumes much less fuel and is better for the engine. The thing is that the block bolted on the front or wings of your aircraft is not really an engine. It's 4 or 6 different engines tied together. Like the horses pulling a stagecoach, you can command, steer, even whip the whole team, but it's difficult without information from each member of the team to know exactly how it's performing. To some extent, an engine monitor provides that information and allows you more accurately to control what's going on. If an owner is interested in the benefits of lean of peak operation, they'll start by using the analytical data from the monitor to balance the injectors to ensure that all the cylinders peak at the same mixture control setting. You send the engine data off to GAMI in the US, and they send back balanced injectors. That allows you to take all the cylinders into lean of peak operation at the same moment, avoiding the lumpiness you get when you weaken the mixture on an unbalanced engine. Having said that, the injectors on my Navajo are original and are balanced as well as GAMI could manage. Generally, lean of peak operation means operating at 50 degrees Fahrenheit cooler than peak, though this may be a bit more or less on different cylinders. I find that on a turbocharged engine, the easiest way to do this is to look at the turbine inlet temperature, as it is the aggregation of all of the EGTs. If you take that to peak and then 50 degrees Fahrenheit cooler, you will have done the best average job. It's important to note that measurement of absolute EGT is not reliable because the placement of probes is so critical. but there is maximum permissible turbine inlet temperature, typically 1650 degrees Fahrenheit, and if that is exceeded, turbo damage is likely. Lean of peak works best with turbochargers. People tell me that it works on normally aspirated engines, but my experience in the Aztec was that power fell away dramatically lean of peak and operation was inefficient. Your results may vary. On my turbocharged Navajo, I get superb results, with fuel burn for the same speed reduced by a third. Lean of peak has every advantage over rich of peak, giving lower cylinder head temperatures and cylinder internal pressure, as well as greatly improved fuel burn and range. Let's now talk about the biggest killer, especially in MEPs, fuel starvation and fuel exhaustion. The silliest way to die in a light aircraft is to go down with engines which have run out of fuel, but with plenty of fuel on board, which is in unused tanks. It seems to me that some Cessna twins in particular are prone to this, and I recommend the accident report on Golf Bravo X-ray Uniform Yankee to anyone with a complex fuel system. 2 people died as a result of a Cessna 310 engine stopping from fuel starvation when there was more than half an hour's fuel remaining in the auxiliary tanks. So it's really important to know the fuel system. This may be obvious in an aircraft you own and fly a lot, but a rental where the checkout has been in the circuit and local area is a different matter. Some aircraft return excess fuel to a different tank from where it started, and if there's not enough capacity in that tank, it will be vented overboard. In others, you need to transfer fuel from one tank to another before it can be used, and that fuel flow may be slower than the burn rate, meaning that the transfer tanks cannot keep up with consumption, making fuel inaccessible. Thus, you can get fuel starvation with fuel on board if you're not on top of your game. When the fuel actually runs out, it's called fuel exhaustion and is the biggest single point of failure, especially in twins. The classic case is the pilot trying to maximize the amount of cheap fuel they can buy in the Channel Islands and ending up in the water a few miles short. I'm all for cheap flying, but ditching out to sea is not cheap. Pushing it to the limits is a gamble. Funnily enough, I'm writing this script in Guernsey, well able to have planned to arrive on fumes, but I refueled before I left Biggin Hill and actually had 2.5 hours of fuel remaining on landing, costing me €300 in lost opportunity. I don't feel lucky. Please don't push it. PPLIR Europe has lost too many friends already. Don't be the next one. Set your final reserve fuel higher than EASA suggests, and now higher again. Finally, replanning in flight. Flights often go as planned. As a summer job, I used to work in a petrol station in the days when forecourts were manned, and the great explorer Ranulph Fiennes would regularly arrive in his E-type and demand exactly the number of tenths of a gallon, and that would be where the pump would cut out every time. Such planning is possible, but wind and ATC routing and delays are not always as we plan, and we might do better or worse beyond our control. If we're doing worse and we're going to be close to our final reserve, we must have a good idea where we can divert, which may or may not be as planned, alternate. But if there's any possibility that the situation might arise, we need to know where is open with the correct fuel, has customs and immigration facilities if required, which is not affected by no terms affecting fuel, opening hours, runway, parking, or nav availability, which has weather reliably above minima, and which is not going to be prohibitively expensive. This information is difficult and time-consuming in flight, so you should put some bolt holes in your back pocket before you leave. And don't forget that en route alternate option. If fuel might be tight going 800 nautical miles, taking routing and contingency into account, then plan for somewhere at 700 miles with a real destination as your alternate. And at 600 miles, calculate whether your contingency is still at hand and allows you to continue. When I did this for a living, we could only continue if the weather was way above minima. There were 2 runways, in case someone crashed on one of them, and no anticipated delays. But under NCO, such calculations are your responsibility alone. Use that discretion wisely. Make sure that ATC understands that your diversion is a change of plan and not an emergency. It won't be the first time they will have heard the situation. This has all been fairly obvious stuff, but it's good to bring it back to the forefront of your mind. Fly safely with plenty of reserve. See you in the next video.